Now let's discuss how to find the coefficients for a simple linear regression model that will fit our points best. The algorithm that we are going to discuss is called ordinary least squares, and let me give you some intuition first how it works. Okay. So in this slide you can see a plot with some points, and we will imagine that we would like to find a line that fits these points best. We can have, for example, we can consider several possibilities. So that's one of these, second, third, and fourth. And then let's try to find which line is best. Okay. If you take the first line, you can see that actually you have 3 points on the top, and then you have a lot of points on the bottom, and some of them quite distanced from this line, right? So apparently it's not the best line, it's not the best fit for this case. If you take the second case, this one, it's actually even worse. You have only 2 on the top, and then most of the points are located on the bottom, and also quite far. Okay. The third case, this one, looks probably a little bit better because many points align very close to the straight line. And then you have 3 points which are very much distanced. Okay. And then if you look at the last case, you can see that even though the points are not lying exactly on the straight line, you have at least 4 points that are very close to the straight line. And then you have these 3 points are a little bit closer now. Okay. So probably this is the best fit. Okay. So if you compare all together, this is how they look like. But can we estimate the fit as a number? So can we calculate a statistic that will tell us how good the fit is? And then if we use this, we can use these statistics to find the best fit. Well, actually we can. You remember that the most important thing for any regression model is how small the prediction error is. Okay. So, for example, if we take this point, the error in this case, it's the distance between the predicted value, which is lying on the regression line, and the real y value, right? So the difference between these two, it's an error of prediction. So we can write it like this. So error, or E, is the difference between predicted and measured value. Now, we have a lot of points, so it means that we have to calculate error for every single point in our sample. And then how to make the best model possible? Well, apparently if we want to fit all points as good as possible, the average error should be 0. But the problem is that the error is sometimes negative, sometimes positive. So if we calculate an average error, we simply will have 0. Okay. And we already know how to do what to do in this case, right? Like we did it in regression. We just need to square it because we are interested only in absolute distance between the points and between the predicted and the real values. So we just take a squared error, and then we don't need to calculate average. We just need to calculate a sum of squared errors and then minimize this. Okay. So if we get the coefficients, if we get the slope and intercept for the line that gives as small sum of squared errors as possible, that will be the best line fit, because in this case we sort of fit all the points as good as possible. The sum of squared errors will be the minimum. Okay. Let's look at our examples and let's calculate a sum of squared errors for our 4 examples. So that's the first example. You can see the errors as a line, as red lines, and then you can see that the sum of squared errors, if we calculate the distance and square it and take a sum, it's 47.53. Okay. Then for the second case, it's 47.94, so it's even worse actually. For the third case, it's 56.44, so it's even worse than the first two. But for the last case, it's 36.70. So that's indeed, if we look at these 4 cases, this gives us the best fit, because the sum of squared errors is the minimum. Okay. Now, how to find these coefficients that minimize the sum of squared errors? Actually, this task can be solved analytically if you remember calculus, and in the next video I'm going to show how it can be solved. However, this mathematics is not necessary if you're just going to use the simple linear regression model. So I can just introduce the way how to calculate coefficients first. So the coefficients that fits your model best can be calculated as following. First of all, you have to calculate B1. It's a slope. Slope depends on 2 things. It depends on the covariance between x and y and the variance of x. So the larger covariance for the given variance of x, the larger slope. Okay. And then you can think if covariance is 0, the slope will be 0 as well. So you will not have any linear regression model, so to speak. Okay. And then if you found the slope, you can calculate this intercept by taking the average of y, average of x, and then you just multiply average of x to the slope and subtract this value from the average of y. That will give you the intercept. Okay. Now let's think a little. Let's recall what covariance and variance are. Okay. So the covariance between x and y, it's the following thing. It's a sum of x minus average x, y minus average y. And then you divide it to n minus 1, right? N minus 1. So that's what we call covariance. And then the variance for x is the following thing. It's a sum of squared distances between the values and the average x, and square it, and then divide it to n minus 1. N minus 1. Okay. Then I don't use these indices I and don't use indices for the sum, just to make this these formulas a little bit better readable. But of course we have x1, x2, x3, y1, y2, y3, and so on. Now look, what if we take the ratio? So you remember that B1, it's the ratio between the covariance of x and y and the variance of x. Okay. Now you see we have n minus 1 in each, right? So if we take a ratio, n minus 1 will gone. So we can rewrite this simply. B1 is, first you calculate the sum of x minus mx, and then y minus my, and then you divide it to the sum of x minus mx squared. Okay. So what you need to do, you need to find the, you need to center x and y values by subtracting the average, and then you need to either multiply the centered x and y values or take a square of x values. So actually you can do it easily, even manually, if you want to, using Excel or similar, if your sample size is not very large. Okay. And then in statistics, these two sums are denoted by using the special notation. The top is denoted by SSXY. So SS, it's a sum of squared values. In this case, we don't have squared values. We just have we just multiply the centered x and centered y values. And then the bottom one is called SSXX. Okay. So sum of squared centered x values. Okay. So this is the formula we are going to use to make manual calculations. And let me show you how it works. In this case, I have a sample. I would like to make a regression between height and weight values. And I have a sample of 5 persons with known height and weight. I made it simple, so the calculations are not very complicated. Okay. What you see in the last line, it's just a sum of these values, so we can calculate the average easily, right? So let's start with the average value. So the average value for x, it's just 850 divided to 5. Which is a simple case, because you can just, you have 5 points, so the 170 will be, apparently it will be the average, right? So 170, okay. The average for y, again, you have 350 divided to 5, or you just take the middle point. That's I made this data in a way so you can do the calculations easily. So it's just 70, okay. Now what we need to do first is to calculate the difference between x and the average x and the y and the average y. So I will just do it here. So x minus mx, we have 150 minus 170, it will be minus 20. 160 minus 170, it's minus 10. Then you have 0 here, you have 10 here, and then you have 20 here. Okay, so this is x minus mx. Now let's calculate y minus my. So you have 45 minus 70, it's 20 minus 25. Then you have 55 minus 70, it's minus 15. Then you have 0, and then you can calculate it easily that you have 15 and 25. 15 and 25. Okay. Now let's multiply these two values together. So we will calculate this x minus mx times y minus my, right? Okay. So 20 times 25, it will be 500. 500, because it's negative and negative, we get the positive value. Here we have 150, then we have 0, then we have 150, then we have 500. Okay. Then we can take a sum. We can take a sum which gives us the sum of squared this SSXY. So it will be 650 plus 650, which gives us 1300. Okay. So this is our SSXY. Now we can calculate the x minus mx squared. Just need to take the values from the first column and square them. So minus 20 squared will be 400. Then minus 10 squared will be 100. Then you have 0. Then you have again 100 and 400. Okay. And then if you take a sum, you will get this SSXX, which in this case you can easily see it's just 1000. 1000. Okay. So now we can calculate the slope. It's just a ratio of 1300 to 1000, which is 1.3, right? So the slope, the coefficient B1, it's SSXY divided to SSXX, which is 1300 divided to 1000, which gives us simply 1.3. So this is the slope. This is the slope. Okay. Now, how to calculate the intercept? Well, we know already the average y and average x, so we need to multiply average x to 170. Sorry, we need to multiply average x to 1.3 and add 70. So I will do it here, and I have some place here. So B0 is when you have 70 minus 170, subtract, of course, not add, times 1.3, which gives us minus 151. Minus 151. Okay. So now we can write the model. So our model tells that if you want to calculate a weight, which is y in this case, you need to take height. You need to take height x, multiply to 1.3, and subtract 151. Okay. Now let's see how the model works. For example, let's do it for 150. Okay. So if we take this one, 150, so 150 times 1.3 minus 151. Okay. So this will give us 44. So you can see that you've got 44 as a predicted value, but the real value is 45, right? So we have an error in this case. So the predicted value is smaller by 1 kilogram than 150 than the real one. But you can see that the model is quite good. The error is quite small, right? And then you can continue and calculate predicted value for every of the white values if you want. Okay. If you look at the model, this is how model looks like, right? So the red line, it's our model. The slope of this line is 1.3 and intercept is minus 151. And then you can see that the points align very close to the straight line. So this line fits our points very well. You can see that we have 2 points on the bottom, these ones and these ones. We have 1 point exactly on the top, of course, not on the bottom. 1 point line exactly on the straight line, and then we have 2 points on the bottom of this line. And you can see that the distance between the points and the line, it's more or less the same. So you can expect that you will have 1 centimeter error, 1 kilogram error in 4 cases, and then in this case where you have a central point, the error will be 0. So the model is quite good because points are very close to a straight line, and the line fits them very well.